Let's say you were hanging around in the city, enjoying a fresh summer evening, having a whale of a time, but then this happened. A blue whale out of nowhere. Let's see, is it still alive? What's that? It died? How sad and tragic. I guess you could say rest in Pisces? Anyway, how on earth are we going to get the whale out of the city? We can't airlift it because it's way too heavy. We can't cut it into pieces either, because whales have a tendency to explode. They can inflate due to the buildup of gases from the decomposition process. Whale explosions can throw chunks of whale flesh up to 240 meters away, so that would require evacuating a lot of people. Not to mention potentially causing a lot of property damage, and also it's very stinky. So, to solve a problem, we need to transport the whale from here to the whale extraction zone, which is all the way over here. However, since the streets are thin, this is going to be a difficult endeavor. Which path should we take? We don't have a lot of possibilities to turn, due to the large size of the whale, so it's easy to get stuck. Going into this street here, for example, seems basically impossible. We can't make this turn, no matter how hard we try. So, to deal with the rotational aspects, we can't use traditional A-star pathfinding. Instead, we're going to use the Rapidly Exploring Random Tree Algorithm, or RRT for short. This algorithm works by building a tree out of so-called configurations. What is a configuration, you ask? A configuration is just a point in 3D space, which describes the current position and rotation of the whale. X is the x-coordinate of the whale, y is the y-coordinate, and theta is the rotation of the whale in radians. A configuration can be either occupied or free. Occupied means the whale collides with a building, thus the whale cannot be in this configuration, and we use a red color. Free means the whale is not colliding, so we use a green color instead. Now, I'm going to explain how the algorithm works, so listen closely. First, we add the starting point, or configuration, to the tree. Then, we pick a random point, and we call it our target point. Then, we find the closest point to it in the tree, which is the starting point in this case. After that, we perform a small step from the closest point towards the direction of the target point, and check if the whale can move directly to this candidate point. In this case, he can't, since there's a building in the way. So we reject the candidate point and try again. We keep trying this over and over again, picking a random target point every time, until eventually we should theoretically arrive at the goal position. Oh look, we found a candidate point that actually didn't collide. So we add it to the tree, connect it to the closest point, and continue our search. Notice how the candidate points will now attempt to connect to a newly added point as well. Damn, that's a lot of candidate points. I hope my computer isn't gonna explode from rendering all this. Notice the amount of iterations on the bottom right. It can take a lot of iterations to find the path. So this isn't exactly the fastest algorithm in the world. But we'll discuss that at the end. Anyway, we're starting to make a lot of progress now. The whale is definitely going in the right direction. If you look closely, you can see a small portion of the lines go straight towards the goal position. This is not a coincidence, it's actually a trick called goal bias. That means there is a 10% chance to sample the goal position, instead of just a random one. This trick helps guide the algorithm in the right direction. Hey, look! We made it to the whale extraction zone. Thanks to the goal bias trick, once there is a direct path to the goal, the algorithm finds it very quickly. Now, all we have to do is to follow the edges back to the start, and we'll know exactly which path we took. Look, he's trying his best, okay? There we go. Well, that path seemed pretty solid, right? Other than the weird rotations at the end. The whale didn't touch any of the buildings at all. So yeah, that's how you move a whale out of a city. The computer scientist way. Now I still wonder, where did that whale come from to begin with? Oh dear. Anyway, I'll end the video with some more potential future improvements for the algorithm, because there is definitely some room there. For example, there are parameters to tweak, such as the step size, the random seed, and the goal bias. It takes a lot of time to find the right value for these though, so tweaking them can become kind of tedious. Additionally, we could switch to the RRT star algorithm. It works pretty much the same as RRT, except there is a path cleanup step at the end. This helps fix those weird rotations you saw near the end of the path. If you're interested in learning more, the Wikipedia page for RRT has a nice summary of the different kinds of variants of RRT that exist in the world. I haven't personally tried messing with any of these myself, but I'd recommend studying vanilla RRT first, and then once you understand how that works, you learn RRT star on top of it. That's all for now. Thanks for watching. If you liked it, be sure to like, comment and subscribe. If you're interested in things like geometry, math, art and game development, you'll probably like my channel. I've recently started to upload more regularly, so stay tuned for more. If you'd like to support me, you can do so at ko-fi.com/boxsite. Or you can click the link in the description. Any support is appreciated. Thanks!